In the last video, we talked about Bernoulli's equation, which, although not necessarily complicated, is very long. And so in this final video on fluid mechanics, we're going to talk about a way to simplify it in particular situations so that we don't have to do quite as much work. So let's consider the situation right here. We have a large open water tank. So in other words, we have a water tank, but the surface is opened up. There's no top on top. It's just exposed to the atmosphere. And we want to know what is the velocity of the water as it leaves this opening down below. It's like a little spigot. So if we open that up, how quickly is the water going to flow out? What is the fluid velocity as it leaves this point? So to be able to do this, the first thing we need to do is probably go ahead and pull up Bernoulli's equation, which we do here. And remember, that compares two different points in the laminar flow. So we'll say point number 1 is up here at the top, and point number 2 is down here at the spigot. Okay, so if we were to do this, there's so many different pieces here. Is there a way we can try to cut this down? And we can do that by making two key assumptions. Well, the first assumption actually really isn't even an assumption. It's just something that we can notice, which is that at point 1, the water is exposed to the atmosphere, and at point 2, the water is exposed to the atmosphere as it's leaving this point. So that tells us that since we're open at the atmosphere in both places, well, the pressure here will be atmospheric pressure, and the pressure at point 2 will also be atmospheric pressure. And that means we can look at this equation and say, well, this is the same as this, so these terms will just cancel out. And so therefore, we can simplify Bernoulli by cutting away those two terms. Now we're just left with 1/2 rho v1 squared plus rho g y1 equals 1/2 rho v2 squared plus rho g y2. So I just rewrote the equation here at the top, so when we cancel out the pressures, this is what we're left with. And the next thing we want to notice actually is a bit more of an assumption, but what we will notice is that the cross-sectional area at the top of this tank, so this big cross-sectional area at the top, should be significantly bigger than that little cross-sectional area with the spigot hole at the bottom. So A1 is much, much greater than A2. So when we do multiple of these, that just means extremely, much, much, much greater than A2. But we know from the continuity equation that if the cross-sectional area of a flow is much bigger, well, then the water should flow much slower. And if it is narrower, it should flow much faster. So what this allows us to do is say, well, the volume flow rate, at point 1 and point 2 is the same. So therefore, if I have the cross-sectional area of 1 being way bigger than the cross-sectional area of 2, well, then the fluid velocity at 2 should be way bigger than the fluid velocity at 1. In fact, so much bigger, we can say that the fluid velocity at 1 is essentially 0. And therefore, we don't have to really consider it. Now, granted, if it was 0, we would get 0 on the side of the equation, and that wouldn't work. But at the very least, we could say it is infinitesimally small, and therefore practically 0. So, to make sure we understand what I'm saying here, when the water flows out of the spigot, it goes at some velocity, whatever that is, that's what we're trying to figure out. But when that happens, there's such a big cross-sectional area here that the water goes down at an extremely, 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 extremely low rate. So low that we can just consider it to be practically 0. Now, if we do that, that means that V1 is practically 0, and that gets rid of this whole term. So I've now cut down the 6 terms of Bernoulli down to 3. Rho g y1 equals 1/2 rho v2 squared plus rho g y2. So once again, I've written our 3 terms here, just what we got from the previous slide, and now we're going to finish this derivation. Well, one thing we instantly notice is that we have rho in each term, so we can get rid of those. So we're left with g y1 equals 1/2 v2 squared plus g y2. Let's go ahead and move this term over to the other side. So now I have g y1 minus g y2 equals 1/2 v2 squared, and I notice I can pull a g out of here, and additionally I've got a 1/2, so I can multiply both sides by 2, and I get 2g y1 minus y2 equals v2 squared. Well, what is y1, which would be this height here, minus y2, this height here? Well, that would just be delta y, the difference in the two heights. So now I have 2g delta y equals v2 squared, and if I want to take this a final step, I square root both sides, and I get v2 is equal to the square root of 2g delta y. And this equation, v2 is equal to the square root of 2g delta y, is known as Torricelli's law, named for Evangelista Torricelli, who was an Italian physicist who studied with Galileo and came up with the idea for a barometer. Now, one thing I should note is that I wrote 2 here. That's really not necessary. It's just v at this bottom opening. So the v at the bottom opening is equal to 2 times g, the acceleration due to gravity, which should be about 10 meters per second squared, and delta y, the height of fluid above this particular opening. So delta y is telling me from the difference between this surface and this surface. Now, to be able to find this equation, now, I want to be careful. We just derived it here, and the derivation wasn't very hard. It's literally just canceling out some terms and rearranging some things. And so we need to remember this is nothing more than a simplified form of the Bernoulli equation. And in fact, when you're doing problems like this, you should start with the Bernoulli equation, which is a more universal equation, and derive Torricelli's law from there, and then utilize it. It's just good for practice sake. But additionally, let's actually look at a quick situation real fast. So let's imagine you had a ball here located at the top of the reservoir, and you dropped it, and you want to know its velocity when it reached the opening here at the bottom of the reservoir. And let's pretend it doesn't get affected by the water, which is literally holding the ball up top, and we drop it. And you want to know this velocity here. Well, how would we go about solving that? Most of you should be very familiar, though it's been a while, that we can literally just use conservation of energy in this particular situation, where I say, okay, let's go ahead and say that we'll make this bottom point y equals 0, because we can define that, and we will say the energy at the top is equal to the energy at the bottom, because energy is conserved in this situation. And at the top, the ball only has gravitational potential energy, and at the bottom, it only has kinetic energy, since we are basically saying that at the bottom, y equals 0, so there's no gravitational potential energy there. Now, if I do that, and we write in our equations here for gravitational potential energy and kinetic energy, mg delta y equals 1/2 mv squared. And let's look at a few things here. First, the masses are going to cancel. I can multiply the 2 across, so I get 2g delta y equals v squared. And if I take the square root of both sides, I get 2g delta y. And if we look at that, that is literally Torricelli's law. So Torricelli's law, although we derived it from Bernoulli's equation, well, remember, Bernoulli's equation is just a restatement of conservation of energy. And this equation makes sense. What this is basically telling me is I have a little packet of fluid here, and it has some mass. Well, at the top of the fluid, the only type of energy it's going to have is gravitational potential energy. And if we define this bottom point as y equals 0, and I look at this piece of fluid as it comes down and then goes out, and I want to know its energy here, well, now it would only have kinetic energy. So if I want to connect the two, I can just compare those, exactly like we just did with the ball. It is no different. Okay, so let's go ahead and just do a quick practice problem. I am pretty much 100% positive you can do this on your own, but let's make sure. So we have a water tank with an open surface, so the density of water is 1,000 kilograms meters cubed. What's the velocity of the water as it leaves the opening? We'll say that the spigot is 10 centimeters above the ground, and the water tank is 1.5 meters tall. So what I want you to do is start with Bernoulli's equation, go through what pieces cancel out, and derive Torricelli's law from it, and then plug in the numbers and figure out that velocity. So go ahead and pause the video, do that now, come back, and let's see how you did. Well, hopefully you gave it a shot, but let's go ahead and see how exactly it went. So first off, I write Bernoulli's law, and I go ahead and say, okay, this will be point 1, this will be point 2, this will be y1 and y2, and this will be v2. And the first thing we need to remember is that, like we said previously, the atmospheric pressure at the top is equal to the atmospheric pressure out here, so this pressure is equal to this pressure. The pressure terms cancel out. First step of the derivation. Next step of the derivation, remember we can assume that this cross-sectional area at the top is way bigger than this cross-sectional area at the bottom. And because of that, we can say that the velocity at point 2 is really, really big compared to V1, and in fact, because of that, we can say V1 is essentially 0. And that allows us to cross out this term, and we are left with this part of the Bernoulli equation, and we can go ahead and cancel out our densities. So you have gy1 equals 1 half v2 squared plus gy2. We rearrange this, and you should get v2 is equal to the square root of 2g delta y. I plug in my numbers, so we have 2 times 10 meters per second squared times 1.5 meters minus 0.1 meters. Remember, those both have to be in meters, so we have to convert 10 centimeters to 0.1 meters. And when we do then plug the numbers in, we should get about 5.29 meters per second. So the velocity of the water at the bottom is about 5.29 meters per second as it leaves this opening. Alright, so what were the takeaways for this pretty quick video on moving from the Bernoulli equation to Torricelli's law? Well, 1, can we derive Torricelli's law by applying simplifications to the Bernoulli equation? Specifically, that we know that the atmosphere is interacting with the water at the top and water at the bottom, or whatever the fluid is, and because of that we can say those pressures are the same, cancel out that term. And additionally, we know that the cross-sectional area at the top is way bigger than the cross-sectional area at the bottom. Because of that, the fluid velocity at the top is essentially 0, and we can also cancel out that term. And then can we utilize the Bernoulli equation and Torricelli's law to analyze systems involving open tanks or reservoirs or things of that nature?